from the center of the Earth, the gravitational attraction decreases with altitude. So we have a free air correction which compensates for the device above sea level. And then we have a topographic correction which corrects for the gravitational and the density of the materials that make up those higher elevation areas. So you don't have much of a topographic correction, say in Florida, where above sea level maxes out at like 18 feet. But here in Colorado, where we max out at 14,500, give or take, we have a different correction for that. The Bouguer correction corrects for the variations in the density of the Earth's materials, but it's incorporated into this topographic correction. Then we have a latitude correction because the Earth is not exactly round. It's fatter at the equator than it is in a great circle around the poles. And tidal correction, which is relatively minimal in the grand scheme of things, but still need to make those corrections. So the Bouguer gravity anomaly map looks an awful lot like the magnetic anomaly map, only instead of measuring nanoteslas, we are measuring milligauss. So it's the changes in the values of milligauss in the measurement of the gravity. These can be done, both of these, gravity and magnetic, can be done with ground surveys. And magnetic ones are often done ground surveys, but the gravimeter readings are usually taken in the air. If you're flying both of these, the magnetometer has to be way out in the back of the plane. It's got to be as far away from the engines as possible, because the engines will develop a magnetic field when they are running. So we got to get way back here. The gravimeter is in the belly of the plane, and it has a little recording device that protrudes through the skin of the plane. This gray line here is the skin of the plane, and here's our protrusion from our machine that's reading it. And so it's reading what's below the plane, not the luggage and the whatever is in the belly of the plane. It's everything that's below the plane. So it can be anywhere. Then we have downhole geophysical, and this is more often than not called e-logs, but they're not all electric logs. So there's some different kinds of logs that they will give you, sometimes spontaneous potential or SP logs, resistivity logs. Those are always run together on the same tool. Neutron, gamma, caliper just measures the diameter of the hole so you can get a sense of what formations characteristics are for caving in. Gamma is recording the naturally occurring radiation. And then there's sonic logs, which we're using more and more often, but the problem with that is they don't have any questions on that, so I wouldn't worry about that too much. And I'm not going to talk about that because they haven't had any questions so far on sonic logs. This table that is in the study manual will tell you the relative deflections. And so let's talk about this a little bit for e-log interpretation, because they will often have a log on there, and they're not going to say interpret this log. They're going to say, where are you going to put the seals in this well, or something like that. So you have to understand what it is that's being shown here, even though they have given you just a log. Now, SP and resistivity are on the same tool, so they're always run together. And they are always presented together, similar to the diagram on the right here. But on the exam, they don't always give them both to you, which doesn't make any sense, because it's like making things harder than it would be in real life, because you would always get them together. So let's talk about the SP and resistivity, and then we'll address these other logs as well. Resistivity increases to the right, and that's obvious when you have a scale at the top, but they don't always give you a scale. So you need to know that the resistivity increases to the right. SP increases to the left, and if you know a lot about E-logs, you know that this isn't always true, but for the purposes of this exam, we'll take it as being true because they're not going to ask about the oddball situations. And so when it's close to the baseline here, or shale line, that's a low value of SP. And that baseline is on the right-hand side. When it is farther away, SP is spontaneous potential. So the farther away it is away from something where it wants to be, the more potential it has, is how I like to think about that. So these peaks here are high SP because they are far away from this baseline. Okay, so shales and clays are going to have both low SP and low resistivity, which means on parallel logs, they're going to be close together. So this, where it's close together, is a shale or a clay. There's another one here, there's another one here, there's another one here before the big resistivity peaks, another one here, another one here. So where they're close together is going to be the shales and clays. Sandstones have high SPs. All these peaks are sandstone peaks. And the resistivity varies depending on what's in the formation fluids. The sandstones and the sands are where you're going to find the formation fluids. And so if we have salt water on our continuum that I showed you a couple minutes ago, it's going to be salt water has high dissolved solids. It's going to have a high conductance, so that means a low resistivity. Fresh water is higher. It's got a higher resistivity, and hydrocarbons were extremely high, so they were way over on the right-hand side of that resistivity conductance continuum. So what's in the formation fluid is going to cause the resistance curves to change, but the SP doesn't change much under those various circumstances. Okay, so limestone is low SP, but very high resistivity. So these are all limestone peaks. Now coal looks just like limestone in the SP and the resistivity logs. So if they don't say anything about coal in the question, and they don't give you any other logs, I would assume it's limestone, because there's far more limestone in this country than there is coal. But if they are saying something about coal in the question, or if they give you some of these other logs, that will help you to determine whether or not it's coal or limestone, then look at it a little bit closer. So when you have coal, you can figure out whether it's coal or limestone based on a density log. Limestone is much denser than coal is. If we have a neutron log, limestone has a low neutron value and coal has a high neutron value. Coal has a high neutron value because neutron logs are looking for hydrogen, and that gives you a high positive, and that means they use it for looking for water and porosities and oil, because there's a lot of hydrogen in all of those. But it also has a high positive for carbon. So you're going to have a very high value of neutron and a low value in the limestone. The gamma logs are looking for naturally occurring radiation. And so we're going to have that be in the source rocks where the uranium is, because the uranium breaks down and creates radon gas. And the radon gas then accumulates in the shale. It gets caught in the non-interconnected pore spaces in the shales and clays, and it absorbs onto the soil particles, so it kind of sticks there. So you'll get high values in the shales and clays and high values in the source rocks, which are going to be the light-colored igneous rocks, like the granitics. Every place else is going to be low unless you have a roll front uranium deposit, but that's pretty rare. So follow the KISS rule, keep it simple, and we're going to only be looking at normal situations and not unusual situations. Okay, so when we're interpreting this, we're going to be connecting the inflection points from one log to another. And if we have 5 logs here, we're going to be doing it for all 5. And so we take our rolling ruler and just roll it down and draw in these lines, which are not exactly in the right place because PowerPoint, bless its heart, will not allow me to put lines exactly where I want them, but close enough for general interpretation here. Once we've done that, we can label those units. This one's done on the side. I usually do it in the middle between them, but it doesn't really matter. And one thing about the resistivity logs is that they kind of look like a strat column, which is showing you the resistance to erosion. Shale erodes back in. And so those are indentations on the resistance log. Sandstone makes cliff faces oftentimes, and limestone makes ledges because it's even harder to erode. And so if you think about resistance to erosion, it will help you to remember the resistance to electricity, carrying the current. So once we've done this, then we can answer questions about this log because we know what these units are. If I have an oil, for example, oil is less dense than water, so it floats on top of the water. And it needs to be trapped by something. So that would be an aquatard, like a shale or a clay. So what this log would look like if I had oil in this sandstone unit, it would be buoying up. It would be buoyed up by the water that's underneath it. It'll float on top, and it'll get trapped by the shale. So the log above would look the same. But once we got down into this sandstone unit, we would have a very high resistivity, particularly at this scale. If this was a 10,000 scale over here, then it might be a jagged edge, but right now it's probably just peg the needle. Once we get into the water that's buoying it up, we're going to get it drop down, and it's going to go back down to what the resistance of the water is. So if it's fresh water, it'll be a little higher, but if it's salt water, it will be a little lower. So lower value on the resistivity curve. So the SP doesn't change much. So this looks a little funny because there's a big change in the resistivity, but there's not much change in the SP. And so this can be a little bit confusing. But just be aware that this will happen when you have oil over water. The water's buoying it up. It's floated to the top, trapped by the shale. But this also happens when you have a freshwater saltwater interface. The salt water is denser, so it's below, and it has a lower resistivity, so it carries the current. And fresh water has a higher resistivity, so you'll get not quite this extreme, but you will get a high resistivity over a low resistivity when you are crossing over between the freshwater saltwater interface. Okay, so this graph or diagram is from KEYS, which is Borehole Geophysics for Groundwater Investigations. There's something similar to this in the Circular 891, and these are all linked on our website, but Circular 891, which is the Coal Resources publication, where they've drilled the hole and they've logged it while they were drilling it, so they have the general lithologies, and then they run all these tools in there. Gamma neutron caliper measuring the hole size, SP resistivity. And so you can use this as kind of a, what would this look like comparison to the graph or the table, excuse me, that I showed you a few slides ago that's on page 8-13 in the study manual for the 2021 manual. Okay, so looking at this, here's coal. What's it going to look like in all of these logs? How about sandstone? What does it look like in all those logs? Limestone, shale, what are they going to look like? So this is a graphical representation of the table that we had a few slides back. All right, so we're going to put in the producing well, and we want to know where to put the perforations so that that's where we draw the water from. The log's already been interpreted for you, but it doesn't say what these units are, so you need to recognize the units. Unit A is sand, but the water's not that good because it has a high dissolved solid component to it. Low resistivity. B is an aquitard. C is a limestone. And the limestone, there's not very much of it. Sometimes it's tight, which means that there's no water in it. Sometimes it has void spaces that have a lot of water in them. Water out of limestone aquifers, I think, tastes pretty crappy because it's got a lot of calcium carbonate in it, and it's got to be treated because of the calcium carbonate. So if I had a higher resistance formation in sand below, which is what I have here, it's got a high SP and it's got a pretty high resistivity, that's good quality water in sand. But the SP hasn't changed, so I'm still in sand, but the resistivity is dropped here. Right at that point, we have a drop in the resistivity, which means that we have a freshwater saltwater interface here. And the saltwater down here below, if we start pumping this and we have our perforations down here by the freshwater saltwater interface, we will shortly be pumping saltwater, and that's not going to be good for our water consumption. So we're going to want to put the perforations up higher. We're probably not going to want to put them up at the top because sometimes you get drawdown and you don't want to pump air. So we'll put it up in this range in here so that we can pump as long as we can before the saltwater intrusion intrudes into our well. Okay, I'm going to give this over to Patty so she can talk for a while. And mute myself.
Yeah, there's some questions that have come into about the e-logs. So the question is, for e-logs, is A, always poor quality water and sand? Let's see.